Okay guys, in this video we're going to look at this problem F4-24. Just before I get there, I just want to have a look here at F4-23. Many of you in the tutorial on Friday were a bit confused with what's going on over here. I just want to remind you that this arrow with the blue arrow going around it, the rotational, the circular arrow, whatever you want to call it, this is the symbol for a moment, right? That arrow is the axis about which the couple moment is rotating, and the blue arrow gives you the center of rotation. So if you put your thumb in the direction of the black arrow, then your fingers should curl in the direction of the blue arrow. Similarly here. So what you've got here are two couple moments. So it says you determine the resultant couple moment acting on the pipe assembly. So all you need to do, because a moment is a vector, all you need to do is convert this into vector form, convert that into vector form, and add up your components, add up your i's, add up your j's, add up your k's, just like we did for forces. So guys, this is not a force, it is a moment, but it's a couple moment. These are two couple moments, and basically, if we look at this example here, we've got two forces. Here we have a couple, right? This is not the representation of a moment. We've got a couple, two forces, same magnitude, opposite direction, and separated by a distance. Similarly here, similarly here, similarly with this example down here. These are all couples, right? A couple are the two forces which cause the moment. But here is a representation of the moment already, okay? It's already in couple moment form. All you need to do is convert it into vector form and add up the components. Now we come to this one. It says here, determine the couple moment acting on the pipe assembly and express the result as a Cartesian vector. Okay? So how do we go about solving this? Well, the one way is that immediately, guys, you can just simply see that we've got this couple of 450, 450, opposing direction, same magnitude, and then there is this perpendicular distance. So in scalar form, what we can do is, it's simply 450 times 0,4. That is the magnitude, right? That's the magnitude. But so the magnitude, obtaining the magnitude is very simple. You've got these two forces. They're separated by this perpendicular distance. And so you've got the magnitude. The direction, however, of this couple moment is pretty tricky to find. Perhaps impossible scalar-wise. No, I don't think it's impossible. But as you can see, this force is going there, that force is going down here. So there's going to be a kind of a rotation like that. And it's an anti-clockwise rotation, which means the axis about which it is rotating is coming up like this. I don't know how best to describe it, but I think you can kind of see, right? Nevertheless, the way to solve this is then to convert into vector form, and then we can solve the direction. Okay, because we can easily find the magnitude. 450 times 0.4 is the magnitude. But what is the direction? Well, we need to convert this into vector form. So, the one force looks like that, 450, and it is perfectly in the ZY plane. Okay, so Z and Y. It's only in the ZY plane, there's no X component, and it has this triangle of 5, 4, 3, and then there's also, so let's convert this one into Cartesian vector form. So that's Newton, right? So if we want F, so it's going to be the magnitude of 450, but then what do we have in the X? We have 0. In the Y, we have what? We have 4 over 5, right? and that has to be negative because it's going in the negative direction. Then we also have plus 3 over 5k. Alright, so we're trying to convert this force into Cartesian vector form, and that's what we get. Then the other one is coming down, and it obviously also has the same ratio, 5, 4, 3. So this one then, FB, this was FA by the way, is then just simply the full magnitude of 450, but what we have is 4 over 5j, and we have minus 3 over 5k. So as you can see, these are simply opposite. That's what a couple is. It's the same magnitude. There's the magnitude, and there is actually the unit vector, by the way, the unit vector. And you can see these are opposing vectors. Okay? So now remember, how do we calculate the resultant couple moment? It's simply, it looks like this, R cross F. All we need to do is take moments about one of the points along the line of action of the force. Okay? Let me come back to the real drawing. So all we need to do is take moments about the line of action of this force, or moments about the line of action of this force. So why don't we take moments about point B? Why would we do that? Because then it cancels out the moment due to this force. So all we need to do is calculate a position vector from A to B, okay? And, I'm sorry, from B to A. We're going to actually, let's take moments about point A, because then we're going to have a positive position vector. You can do either one. So I'm going to take a position vector AB, and I'm going to cross it with this position vector, with this force FB in vector form. So if that's A and that's B, and we know that this distance is 0.4 meters, and it is perfectly in the x direction, okay, because this is the x-axis, then that RAB is going to equal 0.4 I. So our moment is an RAB, our couple moment, cross FB. Remember, just want to remind you that this is that equation. This R, the R that we choose, must always, the F that we choose must always be the R toward which, right, toward which the position vector is going. So RAB is going towards this vector here, which is FB. So we must include FB here. If we were choosing a position vector from there to there, we would need to choose FA. Alright? So then what do we have? We've got this, we've got the I, J, K, and we've simply got 0.4, 0, 0, and we have, let me just, okay, so if we work out this FB, because that's what we want, it ends up being 360J minus 270K Newton. That's what our FB is. So if we put that here, we get, that's a 0, there's a 360, there's a minus 270. And we carry out our determinant. As you can see, we say I, and then the whole moment about the I-axis will be 0, because we carry out our determinant here, 0 times that, minus 0 times that. We're going to get 0, minus J. We cross that out, we've got these four numbers. We're going to have 0.4 times minus 270 minus 0 times 0. We're going to have plus K. We cross that out, we're going to have 0.4 times 360 minus 0. So this will end up giving us 270 times 0.4. This will give us 10,8 in the J, right? Because the minuses cancel out, or when you minus times a minus is a plus. Sorry, that's 108. My mistake. In the J, plus 360 times 0.4 is 144 in the K. So that is my moment. So Newton meter. Okay, so remember, this is now my moment. It has a direction and a magnitude. What is the magnitude? The magnitude will be 108 squared plus 144 squared square root 108 squared plus 144 squared. We end up with 180 Newton meter. That's the magnitude. Now let's test whether this is right. What happens if we take, remember I said earlier that the magnitude was simply the force times that distance, where the distance is the perpendicular distance between the two forces. What happens if we say 450 times 0.4? We get 450 times 0.4 equals 180. So that means that this is correct. That means that that magnitude is correct. We've got a direction now. Remember, the direction was very difficult for us to find earlier, but what we know is that there's no moment about the x-axis. There's no component of a moment about the x-axis, but we have a moment, components of the moment about the y-axis and the z-axis. Okay? So I hope this was helpful. Let us even see. I'm not 100% sure if that is the correct answer. I need to just check in the back of the F problems. This is F4-24, and indeed, that is the answer there. 108J plus 144K Newton meter. So just to remind you, you could take moments about that point or that point. All you need to take note of is that the position vector will change direction and we change the force that we use in our calculations. Okay guys, cheers.